In the reaction written below, the concentrations at 440 degrees Celsius are HI equals to 0.004 molar, hydrogen gas is 0.0075 molar, and iodine is equal to 4.3 times 10 to the minus fifth molar. The question asks us, determine the value of the equilibrium constant at this temperature. Now the equilibrium constant, what they're asking us for is for the KEQ for this reaction. Now whenever you calculate a KEQ, you have the concentration of the products divided by the concentrations of the reactants. Now in this case, the KEQ would equal to the concentration of the hydrogen gas times the concentration of the iodine gas divided by the concentration of hydrogen iodide. But here we square that, because if you look at the coefficient in front of the HI, it's 2. And the K equilibrium says that you raise that coefficient to the exponent of that concentration. If we now plug in our values, then this would equal H2 concentration was 0.0075. The concentration of the I2, we can see in the problem, is 4.3 times 10 to the minus 5 molar. And the concentration of the HI is going to be 0.004 molar raised to the exponent 2. Now, when you do that math, you wind up with a 0.02 value for the KEQ. And that is indicating the degree to which this reaction will go forward. You'll notice that the KEQ value here is very small. Anything less than 1, the reaction favors reactants. I mean, it's not very successful at making products. So in this given case, with the KEQ becoming 0.02, this reaction does not produce much product very successfully. And in the end, that is the reason why the KEQ value is useful. It lets you know how successful that reaction is at making product. Now let's move on. Let's move on to question number 39. In 39 it says that 0.14 grams of nickel 2 hydroxide solid dissolves per liter of water at 20 degrees Celsius and produces a saturated solution. Calculate the solubility product constant for nickel 2 hydroxide at this temperature. Well, that's kind of a mouthful. Bottom line, here's what they're asking us. They're asking us to say if we have 0.14 grams of nickel hydroxide, how successful is it at dissolving? Does it dissolve very well, producing the ions, or does it tend to stay as a solid? We can figure that out by figuring out our KSP. So our first move is we have to get concentrations. But they've told us that we have 0.14 grams of nickel hydroxide. I don't want grams. I want some molarity. So we're going to first convert the 0.14 grams into moles. So 0.14 grams of the nickel is how many moles? Well, what we know is 92.71 grams is the molar mass of nickel hydroxide. So that's the weight of 1 mole. If we now cross multiply, we would find out that we have 1.51 times 10 to the minus 3 moles of the nickel hydroxide. Now, if we know we have that many moles in 1 liter, that is the molarity of the nickel hydroxide. So the KSP is going to equal to the concentration of the Ni plus 2 and the OH minus 1 squared. Now it might help if we were to write this out as a reaction so we could see it better. Should have done that probably at first. So nickel hydroxide is NiOH, but it tells us that the nickel is at a charge of a plus 2. The polyatomic OH is a minus 1. So we're going to need to make that NiOH2. This is going to disassociate into the Ni plus 2 plus the OH minus, but to balance it out, we got to put the coefficient of a 2 here. By knowing this reaction, we know that the KSB will now be the Ni plus 2, the OH minus 1, but because of the coefficient, we have to then square that value. So we can now take the values that they gave us, which is 1.5 times 10 to the minus 3 times 3.02 times 10 to the minus 3 squared. When you grind that out, you will find that the KSP value is 1.38 times 10 to the minus 8. Now what does that mean? That number is saying that you will have a disassociation of the nickel hydroxide, but it will not disassociate very well at all, because this number is extremely small. And it gives you a degree or an idea of what kind of dissolving you can expect.